Thank you for the invitation to giving a seminar. Well, yes, I will not tell you about the scooping of gravitational wave detection with pulsar timing, because this probably won't happen before advanced LIGO. It will probably happen before LISA, so we'll see. So this is a work that I started 2 years ago with Alberto Vecchio at the University of Birmingham, and other collaborators are Marta Volonteri and Carlo Nicola Polaccino in Pisa. And so as you can see, it's a kind of an Italian collaboration because for some strange reasons, Italians get along with Italians, but anyway. So the plan of the talk, briefly, I will give you an introduction about okay, first of all, what are we talking about? Pulsar timing is a technique which is sensitive to gravitational wave at very low frequency. So the natural sources for this detector are massive black hole binaries. So I will give you an introduction about massive black hole binary formation and evolution in the clustering scenario. Then I will talk to you about the detection of these gravitational waves with the pulsar timing, and I will go through the kind of signal you may expect to detect. So our best knowledge up to date of the formation of a structure in the universe is that it proceeds in a hierarchical fashion. So structure form at very high redshift 50, 20 or so. You form the first clumps of dark matter, which dominates the matter content of the universe. These clumps just merge together, and the baryonic component, which is just 10% of the matter, just follows the potential well of the dark matter. So you have the first protogalactic loads in these mini halos at high redshift that start to merge together. And merging together, they form protogalaxies, and then they merge, forming the big galaxies we see today in galactic cluster, for example. So this is a hierarchical process, a process in which you have a lot of mergers between these dark matter halos and galaxies. And we also know today that there are strong correlations between the massive black holes which reside in these galaxies and properties of the galactic bulges, okay? And these are the well-known M sigma and black hole and bulge relation. So in this panel you see, well, these are two quite old plots, but you see the two correlation. This is the black hole mass as a function of the bulge luminosity that you can convert in bulge mass, and is what observational astronomers call a clean relation between the quantities. And here you see the relation between the mass of the black hole and the velocity dispersion of the bulge. So the galactic formation is hierarchical, and these two relations point toward the coevolution of bulges and black holes. So since the evolution of galaxies is hierarchical, also the evolution of this massive black hole has to proceed in a hierarchical fashion, okay? And so simply if you have protogalaxies with seed black holes at high redshift, then the galaxies merge together, and the black holes that are in the center of these protogalaxies are brought to the center of the remnant and merge together as well. So what you expect in this scenario is that you will form, along the cosmic history, a large number of massive black hole binaries, okay? So what happened after two galaxies merge? So the dynamical evolution of the binary can be described as follows. So at the beginning, the two black holes, which are quite far apart, are dragged to the center of the galactic remnant because of dynamical friction, and they form a bound pair, a bound binary. At that point, dynamical friction is not efficient anymore in shrinking the orbit of the binary, and then you have to invoke other mechanisms. This is what is known in the last years as the final parsec problem. There are several mechanisms that may help to overcome this problem. For example, if you are in a dense stellar nucleus, you can scatter stars by means of three-body interaction with the binary. The stars are kicked out and take away energy from the binary, and this shrinks the orbit. But you can have also other mechanisms. You can have a circumbinary disk, gaseous disk, which exert torques on the binary, which help to shrink the orbit. So there are several mechanisms which are proposed to overcome this problem. Okay, this is still if this problem is overcome or not is still a kind of an open question. People think that in the end this binary will merge. Okay, but for sure, if you can reach a sub-parsec scale, like 10 to the minus 2, 10 to the minus 3 parsec separation for this binary, at that point gravitational waves emission become efficient, and this leads to a fast coalescence of the binary. Gravitational emission takes over because we know that each mass, every mass which quadruple momentum, okay, varying in time, is an emitter of gravitational wave. Okay, so I don't have to spend time on this. A gravitational wave can be described as a ripple in space-time propagating at the speed of light, basically. And if you have two massive black holes, which are basically the most massive and dense objects in the universe, orbiting each other, this is a huge quadruple momentum varying in time, and these are the strongest gravitational wave sources we may expect to observe in the universe. Okay? So we have a lot of galaxies that merge together, we have a lot of massive black holes that coalesce together, so we expect to have a lot of gravitational wave sources. So gravitational waves can be described as waves, exactly as electromagnetic wave. Okay, kind of different, but basically the same thing. And so you can build a spectrum. The spectrum of gravitational waves basically cover 20 order of magnitude. From the inverse of the age of the universe, you expect a signal from inflation, for example, in this case, up to kilohertz or so. And so here you see this spectrum. You see on the top the sources you expect to detect in the spectrum. And you see that on the bottom you see that we have several ongoing and upcoming experiments to probe different windows in the spectrum. For example, at the very high frequency, at the kilohertz or so, we have the ground-based laser interferometers like LIGO or Virgo, and they updated version which will come online in 5 years or so, like advanced LIGO. And these are expected to be sensitive, for example, to coalescence of compact objects like stellar black holes or double neutron stars or objects like this. Moving to our lower frequency, there are two frequency windows which are of interest for us, which are LISA, which is going to probe the milliards frequency band, and the precision timing of millisecond pulsars, which is a technique which is sensitive in the range between 10 to the minus 9, 10 to the minus 7 hertz, so nanohertz, okay? If you consider a massive black hole binary which emits gravitational wave and shrinks its orbit in time, okay, you expect basically, for example, suppose you have a circular binary, you expect a single harmonic, an emission of a sinusoidal with a single harmonic, but the frequency of this wave will increase in time. So as the binary shrink, the frequency spectrum it emits sweeps toward higher frequency. Okay, and if you do the math, basically you consider a typical massive black hole binary, you see that the frequency range that you expect to cover during this shrinking is something between 10 to the minus 10 hertz to some millihertz or 10 to the minus 2 hertz or so. So basically, pulsar timing will be sensitive to the early stage of the shrinking of these massive black hole binaries. Okay. So what is pulsar timing? So basically, pulsar timing aim to detect gravitational wave taking advantage of monitoring of millisecond pulsars. So millisecond pulsars are fast-rotating neutron stars, which emit a beam radio jet, basically, and each time this radio jet points toward us, you see a pulse. Okay, these were found to be the most stable clocks in the universe. Okay, so these pulsars are very stable, and what you can do, basically, you can record the time of arrival of the pulses of this pulsar, and if you have a gravitational wave passing through, So basically, you see the signature of the gravitational wave into the time of arrival of your pulsar. This is an idea that goes back to the 70s, and people started to work onto this idea. And today, many different collaborations are trying to seriously probe gravitational wave with this technique. So there are three different main collaborations. One is the PARCS Pulsar Timing Array, which is the Australian collaboration, which is the more advanced right now. They are already monitoring 20 millisecond pulsars with a very good precision level. And their aim is to detect some signal in the next 5 to 10 years with this array of pulsars. But also the North Americans are moving. Now there is NanoGrav, the North American Nano-Earth Observatory for Gravitational Waves, which is starting to collect the data using, among the others, the Arecibo Radio Telescope. But also the European now have their collaboration, which is LEAP, the Large European Array for Pulsars, which aims to take advantage of the 5, well, now 4, but soon there will be 5, 100-meter equivalent radio telescope spread around Europe. Okay? So there are these three collaborations that they are supposed to join, to exchange data and join each other in the next year in something which would be something like the World Pulsar Timing Array. But this depends also on politic stuff, and I don't know if it's going to happen or not. But, so going a little bit into the details, so how you detect this gravitational wave in practice? In practice, what happens is that if you have a gravitational wave passing through the line, passing through basically the path of the pulse from the pulsar to you, what you see is the phasing basically in the frequency of the pulses. Okay, and if you do the calculation, what turns out is that this dephasing depends on the strength of the gravitational wave at the Earth minus the strength of the gravitational wave at the pulsar. So basically, you have the Earth, you have the pulsar, both are shaken because of the gravitational wave passage, and you detect basically the difference of the shaking. Okay? So since you are timing an object, the actual observable in this game is the timing residual, which is basically an integral over the observation time of this frequency phase. Okay? And if you do a back-of-the-envelope calculation, you have a wave with a certain strength h. Okay? You have an integral over time. So basically, the strength of your residual as an order of magnitude is the amplitude of the wave over the frequency. Okay, more or less. And if you plug in typical numbers for massive black hole binaries, 10 to the 9 solar masses or so, at redshift less than 1 or something like that, the typical order of magnitude of that quantity is between a nanosecond to hundreds of nanoseconds. Okay? So this technique was already, for example, used a few years ago to rule out presence of a very massive black hole binary proposed by Sudo et al. In 2003. So they proposed something like a 10 to the 10 chirp mass massive black hole binaries in a system at 80 megaparsec away from us. And okay, if you have a system like that, it emits gravitational waves, okay, and you can calculate the residuals. And if you do that, this is basically what you find. This is what the data stream on a single pulsar would look like if this massive binary would emit gravitational wave, would be there. So you see, this is the time in years. This is the residual in microseconds. Okay, and this is the signature of this massive black hole binary. Okay, which is basically a 10 microsecond residual, which is a huge signal because now pulsar timing array, pulsar timing, some of these pulsars are monitored to 100 nanosecond precision. So if that binary would be there, we would observe it. Okay, this is what you expect to see. This is what you see. Okay, and if you study this signal, if you do the power spectrum, whatever you want, you don't find any signature of any periodic wave like that. So this is the first example of how pulsar timing was used a few years ago to rule out a possible, but still quite debated at the time, already quite debated at the time, astrophysical source. Okay, this is what happened for if you have an individual binary. but if you have a collection, if you have a whole population of merging galaxies, you expect to have a whole population of binaries. And this population of binary would give you a signal, a lot of signal that basically will superpose each other, okay? And so what does, how does this kind of signal look like? It looks, this is described in this slide. Well, I don't want to go into mathematical details. So basically, I just want to point on this formula here. So suppose you have a population of massive black hole binary described by a certain differential number of binaries per unit redshift, unit chirp mass, unit frequency, okay? So basically, the characteristic strain of the gravitational wave signal emitted by this population of binary, what's that? This characteristic strain is nothing else than basically the integral over redshift and masses of the signal emitted by each single source. Okay, nothing surprising. So if you have a certain number of binaries, you just basically sum up the signal from each binary in quadrature, okay? Which is nothing surprising. This is well known. And the typical level of the residual given by this population of binaries is basically the characteristic amplitude over the frequency, okay? And if you consider the form, the mathematical form of the amplitude emitted by each single source, and you plug in numbers and dependencies, what turns out is that the characteristic frequency, the characteristic amplitude goes with the f with the frequency to the minus 2/3. And this gives you a well-defined shape also in the spectrum of the residuals, okay? And so you expect to observe a very a very red spectrum, okay, given by this population of binaries. Okay, but we want to do some prediction for these radio astronomers that monitor these pulsars. So what you need to do prediction is basically an estimation for that guy there. The number of the differential distribution of binary per unit redshift, unit mass, and unit frequency. To do that, you can employ different techniques. We used two different techniques. One is tracing the evolution of massive black holes during cosmic history using semi-analytic merger trees based on the extent present Schechter formalism. And the other was using catalogs of merging galaxies extracted by the Millennium simulation, okay? For this type of work, this second tool is probably more useful because this simulation is this is a huge simulation of a huge co-moving volume of the universe. Okay, so it gives you a large statistic of massive objects at low redshift. Okay, because with this pulsar timing, what we expect to see are binaries of 10 to the 8 solar masses or so at redshift less than 2 or so. Okay, so we need the statistics on the big objects at low redshift. Okay, so basically this is the best tool so far to do something like this. So what we did was to go online, okay, and take one of the semi-analytic catalog of galaxy population that are employed on the Millennium Run, and just populate these merging galaxies with the black holes according to different prescriptions. To sample, what happens if you consider different relation for the M black hole and Budge relation or M black hole sigma relation, if you consider different accretion route for the black hole or so. So in the end, what we did, we extracted several catalogs, okay, of merging binaries from the Millennium Run, okay, and each of these catalogs is a different model for black hole, for this population of black hole and its evolution. Okay, if you do basically an analytical estimation of that integral there, you just find something like this. This is just to show you where the main contribution to the signal comes from. So this is the characteristic amplitude of the signal as a function of frequency in the frequency range relevant to pulsar timing. And so from this this plot here, you see that basically 90% of the signal come from binaries which have chirp mass larger than 10 to the 8 solar masses and are at redshift less than 2. So what we are doing here with this technique is probing very massive, cosmologically nearby binaries. So in some sense, this tool is orthogonal to LISA. Okay, so with LISA, the majority of sources of LISA are expected to be much lighter binaries. Okay, 10 to the 4 to 10 to the 6 solar masses at redshift 5 or so. Here you probe basically a completely different regime of the evolution of this object, of the massive black hole binaries. So I say this because so it's clear that Pulsar timing doesn't want to scoop LISA. It's just probing something else. Okay, both instruments are useful, and we need both of them. Okay, to study the population of these sources. Okay, but this is just an analytical estimation. What you do in practice, you populate your catalog with massive black hole binaries, and then so you have a certain distribution of massive black hole binaries, and you know how many of them, you do the integral, and you know how many massive black hole you expect to have in the universe. And what you do then, to do a single realization of the universe, you just do a Monte Carlo realization of your distribution. So you have a certain number of sources. You don't have infinite sources in the universe. And if you do that, and you compute the signal, this is what you find. So the first thing that you notice is that the signal is not smooth at all. It's not a gentle power law with a given index. Okay? And the second thing is that if you consider something, well, what you can, expect by eye to be the confusion level of this signal here, is something that at high frequency is much steeper than f to the minus 2/3. And on top of that, these are different realizations of the same black hole population. You have single individual spikes given by particularly massive nearby sources. Okay? So basically, you find a signal that is quite different from the theoretical smooth expectation, and this is just so I don't want to go in the mathematical details, but it's just a simple sampling issue. So basically, if you consider your characteristic amplitude, basically is given by the sum of all the sources emitting in a frequency bin, okay, which is the inverse of the time of observation with your array. Okay, so basically, what happened is that when you go toward high frequency, okay, you are losing massive binaries because the binaries, because the lifetime of the binary in a given frequency bin is proportional to the frequency to the minus 1/3. So you have many binaries at low frequency, okay, just few binaries at high frequency. When you sample your population of binary with a finite number of sources, then basically the chance to have one massive binary emitting at high frequency, okay, is basically 0. And this basically forces you to lose power at high frequency. So it's just a small number sampling issue. Okay, it's nothing mysterious or nothing like that. And so what we did was to compute the level of this background for different model and to change the parameters of the merger trees and whatever, and find some analytical prescription of this for this background. So it turns out that this background is well described by a double power law with f to the minus 2/3 at low frequency and going to f to the minus 1.5 or something like that at high frequency with a break around few 10 to the minus 8 hertz. And what is plotted here is basically in red is the uncertainty range of this background, which we found from our models. And the dashed black lines are sensitivities of different pulsar timing ongoing and planned experiment. So the upper one is the current limit, the timing of the best current limit we have from timing of pulsars now is basically that curve over there, which is a factor of 3 above the most optimistic signal we may expect to detect. Okay, but The curve that you see below is the complete Parkes pulsar timing array, which aims to monitor 20 pulsars at the 100 nanosecond level, okay? And you see that this will be sensitive to most of the parameter space of our models. So with the complete pulsar timing array, you will be probably able to detect this background, or at least to rule out several different scenarios for black hole formation and evolution at massive black hole at low redshift. And the lower curve is SKA, the square kilometer array, which is something that will be probably on LISA timescales, so 10, 15 years. And with this instrument, you will be, so if this population of massive black hole exists, you will get the signal in any case. And you will also be able to study the shape and the characteristic of the spectrum, okay? Okay, but I show you that, so this is for the background, but I show you that there are spikes that rise above this background, and you may expect to detect that spikes as individual sources. So what we did, we had these catalogs, we had the distribution of massive black hole binaries. What we did was to do several Monte Carlo realization of this population and study the statistics of the single sources. And so this, I want to show you 1 second the typical, to describe 1 second the typical situation. So before I show you characteristic amplitude, but you can convert characteristic amplitude to timing residual just dividing by the frequency, basically, okay? And this is what I show in the upper left panel, so don't bother about the others. So basically, in that panel, each asterisk is a single massive black hole binary, okay? It's the residual in nanoseconds as a function of frequency, okay? So this is a realization of this population of binaries. What you see here, you have a whole population of binary there, which build up a signal that you cannot deconvolve, okay? And they give you, and all the signal give you a certain confusion level, which is basically the black line over there, which is the level of the signal which you cannot decompose in single sources. But you see that above this level, there are several asterisks which are individual sources that are quite massive and nearby, and you may detect them above the background. So when you try to do that, so what we did was to study the statistics of these sources, and this is the result. So, for example, you can concentrate on the left, for you, right, panel. Okay. So this is the cumulative number of sources as a function of timing residual. Okay. So this tells you the number of individual sources you will be able to detect with your pulsar timing array, given the total sensitivity of your array. Okay. So, for example, if your array have 1 microsecond sensitivity, you have no chance. Okay, you have a chance that is less than 10 to the minus 3 to have this individual binary at that level in the universe. Okay, but if your array sensitivity is 10 nanoseconds or so, you see that all these curves, which are different models for massive black hole formation and evolution, predict at least one individual source. And if you will be able to go to a nanosecond level precision, you will be probably able to detect, to deconvolve a dozen of individual sources in each of these models. Okay, so basically, the nanosecond precision level is probably the goal of SKA. Basically, few nanosecond precision level. With that instrument, you will be able to observe, most probably, a dozen of individual massive black hole binaries in the cosmologically local universe, so a redshift less than 1, 2, or so. Okay? Time? Half an hour. It's too much.
What is the medical limit for the basic precision of those classifications? Do you have any as good as 1 nanosecond?
No, not yet. Now so people I think don't know if at that point they will hit an intrinsic limit of stability of the pulsar. This is something that is not known. But there are now, for example, they have a pulsar in the Parkes pulsar timing array which is monitored to a 50 nanosecond precision. just for 1 year, so they have to increase the number of observations with year. But what I show here is the total equivalent sensitivity of your array. So you don't need a single pulsar to one or few nanoseconds. What people actually think they will be able to do with SKA is to monitor something of an order of 100 pulsars or so at 50, 20 nanosecond level. Okay? So if you do that, if you have, for example, 100 pulsar at 20 nanosecond, then the equivalent sensitivity of your array is something around 2 nanoseconds. And people are quite confident that they will be able to find several pulsars which are stable enough to do that. But the intrinsic limit given by evolution of the pulsar, internal things that happen in the pulsar that are unknown. Okay, so this is just to iterate what I told you before. This is the statistics basically of the chirp mass distribution and redshift distribution of these individually resolvable sources for different models. So as you can see, all the distribution are peaked around something 10 to the 8 solar masses chirp mass. So you're probing the very massive guys, okay? And the redshift distribution, most of the sources are in the redshift range 0.11, okay? So massive nearby sources, okay? Okay, what you do if you, okay, the subsequent natural step to do, you have an individual source, you have your detector, which is your timing array. You try to see to a first order which are the information that you can extract about that source if you detect it with your array. So what we did, well, what we are doing actually, is to do a first simple estimation of how well you can determine the parameter of these binaries once you detect one of them with your pulsar array. Okay, and to do that, we just employ the basic Fisher information matrix. Yeah, Michele is not happy with that, but the Fisher information matrix technique as a first guess of the parameter estimation. So, how does it work? Okay, you have your signal, which is basically a sum over A is the two polarization of the sources of your. It's a sum of a polarization of your gravitational wave. Basically, delta H is basically the H at the pulsar minus H at the Earth, or vice versa. And your residual, which is your observable, is an integral over time of that quantity there. Okay, where the F, which are the antenna beam pattern, that tells you basically how sensitive is your pulsar to a source with a given position in the sky. These antenna beam patterns depend on the relative orientation of the pulsar in the sky and the source. Okay, so you have a signal which depends on the parameter of your binary and depends on the relative position in the sky of your pulsar and the source. Okay. And if you compute this, well, first of all, as a first computation, we did some assumption of our sources. Okay, we just consider circular, non-evolving sources. So you have a single harmonic, okay, and the source is not evolving in time. So this assumption is, I would say, half justified, because at least in my opinion, there isn't any convincing argument that tells you right now that sources, that massive black hole binaries emitting at that frequency has to be circular. And in fact, we know that hardening of a binary in a stellar background most likely is going to increase the eccentricity. And also, now it seems that also resonances in circumbinary disks are going to excite eccentricity in the binary. So we have no clue, actually, how is going to be the eccentricity of these sources. Okay, but as a first guess, as a first attempt, you can consider these sources circular. About the fact that the sources are non-evolving, this is a quite justified assumption because these are massive binaries, okay, quite far away from coalescence. Most of them will coalesce in 10 to the 4 to 10 to the 6 year. And the frequency sweep during the frequency drift during if you observe the binary for 10 years or so, a frequency drift during this 10 years is typically 10 to the minus 13 hertz or so. So you can consider them monochromatic and non-evolving during your observation. And another important assumption we did, we consider only the term, the residual term at the Earth. So as I showed you before, the residual in each pulsar is given by a term given by the gravitational wave at the Earth and the term given by the gravitational wave at the pulsar. So what happens is that if you have several pulsars and you correlate the signal among them, okay, all the terms at the Earth in each pulsar will be correlated and at the same frequency, okay, and they will build you, a peak, a single harmonic at that frequency. But terms at the pulsars will be at different frequency because the shaking of the pulsar that you are detecting now is the shaking given by the gravitational wave passing thousands of years before. So because the pulse has to travel from the pulsar to the Earth, okay? And so what you will have a peak of signal at a given frequency, which is the frequency at the Earth, which will be correlated among all the pulsars, and different signals at different frequencies in each pulsar, which will be much harder to detect. So as a first, for this first case, you can just consider the term at the Earth, which will be correlated among the pulsar, and so it will give you a strong signal at a given frequency. Okay. So these are our assumptions. If you do these assumptions, the residual reads like that. Okay. So basically, it's a function that depends. You have an amplitude R in the front. Then you have your antenna beam pattern that depends on the relative orientation of the pulsar and the source, your initial phase, and all these things. So in the end, your signal depends on seven unknown parameters, which are an unknown amplitude, sky position, wave polarization, inclination of the source, frequency, and initial phase. Okay, so you have seven parameters. And, well, from this, you can compute the error box in the sky with this formula, which consider the theta and phi accuracy in the sky position. Okay? And
but you consider that non-evolving. Do they evolve within a distance to the pulsar?
oh, yes. This is the reason why you consider only the term at the Earth. Because typically the term at the pulsar will be at a different frequency. And all the term at the pulse and at all the pulsars will be all at different frequencies. Because the time delay for each pulsar will be different. So this will be, so if you have, for example, if you have 100 pulsar and you have a signal which, and you have to correlate the signal between 100 pulsar, so it will be much easier to detect the correlation peak of the term at the Earth than the single the individual signals at each pulsar, which will be at a different frequency. Okay. So this basically is just I mean, this is just a simplifying. It's something that you can do. You just consider the term at the Earth, and that term will be monochromatic during your 10 or 20 year observation, because the evolution during 10, 20 years of this binary is 10 to the minus 13 hertz, something like that. Okay. So to estimate the parameter, we employ the standard fission information matrix formalism, where so basically we consider the correlation matrix. So alpha here is an index that alpha is the index. Okay, it's an index related to the pulsar. So alpha is a given pulsar. Okay. So your fission information matrix for a single pulsar would be just basically the inner product of the derivative of the signal with respect to the parameters, where the inner product is defined in the standard wave here, in the standard way here. And if you consider detection using m pulsars, because you will not have a single pulsar, you will have an array of pulsars, then the total fission information matrix of your array will just be the sum of all the fission information matrix of each single pulsar. So you build your matrix, you invert your feature information matrix, and hopefully the terms, in the diagonal terms, will give you basically the 1 sigma errors in the estimation of your parameters. Okay?
So you assume some correlated noise for the different pulsars.
Yes.
Different observations, different telescopes.
No, you just assume, in this case, we just assume that all the pulsars are as an equal noise level, white noise, Gaussian, stationary, whatever. Also uncorrelated, yes.
But it's a reasonable assumption.
Well, that the noise will be uncorrelated, yes. That the noise will be simple, you have to work on that. But this is the first, as a first assumption, what you do to do this kind of estimation.
But the second one is easy to correct. I mean,
Sorry?
it's easy to use a different level for each one. It's not.
Oh, yes.
Just change the number.
Yes. So yeah, I think yes. In this parameter estimation that I'm showing now, we consider that each pulsar has the same noise level. Basically, each pulsar contributes equally to the feature information metric, basically. And okay, what we did was to consider several distribution of pulsars. We consider different isotropic distributions in the sky, increasing the number of pulsars from 3 to 1,000 or so. And we consider an isotropic polar distribution, so just covering a pole with pulsar and then spreading the pulsar all around to see, covering all the sky to see how the sensitivity changes with the distribution, with the sky coverage of your array. And then we also consider the Parkes sample of the 20 millisecond pulsar, which are monitored with the Parkes telescope right now. And for any distribution of pulsar, we just generate a random sample of gravitational wave sources in the sky, considering different polarization, sky polarization, inclination, whatever. Okay, and well, in this particular case, basically the amplitude of your signal is just normalized in order to provide a given signal-to-noise ratio in your array. Okay. And for each of these distributions, we compute errors for each source, and we evaluate the median values, etc., etc. And these are the results. So let's focus on the left panel, upper left figure. So what you see there, the dashed curve with points, is basically the sky accuracy of your, the sky location accuracy of your source in square degrees as a function of the number of pulsars in your array for a fixed signal-to-noise ratio of 10. Okay, so whether is the number of pulsars in the considered in the x-axis, the signal-to-noise ratio of the array is always maintained to 10. Okay, so this tells you how the sky location of your source improves, adding more pulsars to your array. And so you see that for if you have 3 pulsars in your array, basically the sky position of your source is undetermined. Basically, you have a few thousand square degree error box. But if you increase the number of pulsars to 100 or so, then your typical error box with a signal-to-noise ratio of 10 is of the order of 30 to 50 square degrees, which still is big, especially if it's compared to typical error boxes for LISA. But remember that here we are considering 10 to the 8, 10 to the 9 binaries at redshift less than 1 or so. So for example, for a putative search of a counterpart, this will probably be a much easier challenge with respect to the LISA ones. Okay, because if you have a counterpart, will be a very massive source, and if it's accreting or whatever, you can point whatever you have in that sky. You can monitor that sky location even if it's big, because you know that your counterpart will be a big galaxy at low redshift, so there are not millions of them. Okay, even if the sky position is 30 or 40 or 50 degrees, which is quite a nice result. And the black curve, the solid curve on the same panel, basically shows you how the sky position accuracy improves with the signal-to-noise ratio. So now on the x-axis, you you read the signal to noise, and we fix the number of pulsars to 100, and so you see that the sky position accuracy improves at the signal to noise ratio squared, so which is not a surprise. This is for the sky position, which is probably the most important parameter for the sources, also because you can see that there is not that much you can tell about the others. For example, since the sources are not evolving during the evolution, you cannot deconvolve the masses and the luminosity distance of the source, for example. And what you can estimate is an amplitude, which is a combination of these, that you see on the upper right panel. And you can, so the delta R over R is of the order of 0.3. So the theoretical expectation would be 0.1 for a signal to noise ratio of 10. But since basically the amplitude is degenerate with the inclination of the source, the typical accuracy to which you can determine this parameter is 0.3 or so. So you don't get much information about the masses and the distance of the source. You get some more information for astrophysical purposes about, for example, the inclination and the polarization, which gives you basically the orientation of the source in the sky with respect to you. These are typically determined within a factor of 0.3 radians, which is, is quite a big error, but tells you something about the inclination of your source in the sky. So if you have to detect a counterpart quasar or something like that, you can relate the orientation of the sky to the emission. You can do something. On the other panel, I show basically the sky position, the parameter estimation accuracy as a function of the coverage of your array, of the sky with your array. So basically here, 0.1, you have all your pulsars in 0.1 steradian, okay, region. And then you spread the distribution around, and here you cover all the sky, okay? So as you can see, the sky position accuracy improves basically linearly with the sky coverage of your array. So this is the reason why it's important to have pulsars spread all around the sky. And this is the reason because it's important that also the groups of the north hemisphere will join this project of hunting pulsars, because, for example, the Parkes pulsar timing array has 20 millisecond pulsars in the southern hemisphere. Okay, but if you get a source and you want to determine its parameter, it's better if you have pulsars spread all over the sky. Sorry? The observation time? Is 10 years. This is here we assume 10 years monitoring of your signal. Well, I can skip this. Okay, this is just to show you the sky coverage of the array. So this contour map basically shows you the sky position accuracy in the sky of the source at a given point for different distribution of pulsars. So in the top panel you have all the pulsars that are concentrated in the pole, and you see that basically you don't have any sensitivity in all the equatorial region. Okay, you cannot determine the position of the pulsar there, of the source there. But as you spread all the pulsars over the sky, then your sensitivity improves. And here is the limit in which you have 100 pulsar spread all around the sky, and the typical sensitivity in this case is 40 square degrees. Okay, in this WMAP-like map. And so this is for numbers lovers. These are basically the number that we find, and that will be probably published at some point. So, for example, so the main, the typical scenario that one have to consider in this case is, okay, SKA 100 pulsars of all sky, okay? And the numbers are this, in this row here, or, well, more easily this one, okay, which is the same. So you have 40 square degrees calculation accuracy, and you can determine well, the amplitude of the signal to a factor of 0.3, and you can determine the inclination and the polarization of the wave within a 0.3 radians. Okay. Sorry?
The mass is in M is in million. No, M is the number of pulsars.
M is the number of pulsars, yeah. You use to monitor, to detect the signal. And here the signal-to-noise ratio is fixed to 10. And all the quantities scale linearly or quadratically in case of the sky position with the signal-to-noise ratio, of course. And okay, we also consider the Parkes pulsar timing array. So here, just look at the upper panel. So this is basically the sky observed by Parkes. Okay, the 20 black crosses that you may see around there are the locations of the 20 millisecond pulsars. Okay, and here I just basically plot a contour plot of the sky position accuracy of a source observed with that 20 pulsars with a signal-to-noise ratio of 10. As you can see, you have a decent sensitivity in the Australia, in the southern hemisphere. I missed the word. In the southern hemisphere, okay, down to 50 or also even 20 square degrees in some case. But you don't have much sensitivity in the northern hemisphere, where if you have a source there, you can just locate there with a few hundred square degrees precision, which is pretty bad. So this is the reason why we need observation in the northern hemisphere, because having just few pulsars spread around there will improve a lot these capabilities in the future.
So you have the maximum sensitivity when the pulsar is on top of the source?
When the pulsar is very near to the source, yeah.
Is there a simple way to understand that? We know.
No, probably there is, to think about that. The signal is surfing on the pulsar. This is how do you fit that? But yeah, there should be a straightforward way to understand why it's like that. But this is what it is. Yeah. Typically, when the pulsar is close by to the direction of the pulsar is close to the direction of the sources, there is where you have the maximum sensitivity. And okay, so this is it. And in summary, future pulsar timing array will most likely detect an unresolved background from massive black hole binaries in the very massive black hole binaries in the nearby universe. This background spectrum can be fitted by a double power law with a break around 10 to the minus 8 Hertz. But okay, detecting a background is nice and whatever, but people also want to detect a real gravitational wave from a single source. To do that, you need a much better timing precision with respect to what is achieved now. And what we find in our models is that 5 to 15 nanoseconds should guarantee at least the detection of one individual source. Okay, and we try to do some work on the parameter estimation for these sources, and typically we find with the SKA typical configuration of 100 pulsars spread around the sky, you may be able to locate the source within 40 square degrees if it's detected with a signal-to-noise ratio of 10. And of course, all of this is nice, but there were a lot of assumptions. First of all, we considered the binaries to be circular, but we don't actually know. And if binaries are eccentric, then you have emission in a whole spectrum of harmonics, and this is going to affect your signal. But we are working on this, so we are now doing more general models, including self-consistent eccentricity evolution for the binaries according, for example, to stellar dynamics. We have some results already, we just have to process and analyze everything. And we also suppose that binaries lose orbital energy by means of gravitational wave emission only. But if you have this gravitational wave emission is extremely inefficient at low frequency. So if you go to frequency around 10 to the minus 9, And if you have some other fast mechanism to shrink the orbit, for example, a circumbinary disk, okay, at that point the evolution of the binary would be driven by the circumbinary disk and not by gravitational wave. Okay? So the evolution will be faster, so you will have less binaries in that frequency range. And this is going to flatten, basically, your signal at those frequencies. But we did some preliminary estimation. To do that, you need a mechanism which is effective in shrinking the orbit on a million-year timescale, which is pretty fast. Okay, so it's quite unlikely that it's going to happen. But just for fun, here what we did is to consider few. We put few of these massive black hole binaries in triple systems. Okay, if you have a triplet of binary, you can drive the eccentricity of the main binary to a very high values, something like 0.99 something. And at the point, they would emit a burst of gravitational wave during the periastron passage. And this is what can happen. So you can have basically some bumps like that, what is shown in these panels, bumps like this. These are all the harmonics emitted by this binary, given by this very eccentric binary. That is going to affect your signal. So things like this can happen. And this is something that we plan to do in the future. So what we are doing now is track self-consistently the evolution of the binary, consider all the relevant physics, and so track also self-consistently the eccentricity evolution. And then we are also working on the detection, and we are doing more work on the parameter estimation to understand what actually you tell of these sources and what astrophysics you can do with that if there is a chance to detect some reasonable counterpart or stuff like that. So I think this is it. I leave you with the landscape of gravitational waves from massive black hole binaries with our two future probe of this parameter space, of this landscape, which is LISA at relatively high frequency, which will probe the spiral of individual sources quite light, 10 to the 4 to 10 to the 7 solar masses, maybe at high redshift. The bulk of the source would be a redshift 5 or so. And then you have all the signal built at low frequency given by a whole population of binaries, massive binaries, which are still quite far apart, that build this confusion level and which you're going to probe, hopefully, in the future with this pulsar timing array technique. Thank you.